Welcome back to Rocks for Jocks. My name is Alex and I am your host for the show. Today we'll be going into the final part of my summary and review of the book, The Theory of Everything by Stephen Hawking. Have you ever wondered how the universe works? Well, that's what this book is about. Do yourself a favor and listen to parts 1 and 2 when you get a chance. They are not necessary to listen to this episode, but I think they definitely help and have a lot more interesting information. If you find yourself enjoying the show, I'd love for you to hit the pause button and then hit the subscribe button on Spotify or Apple or YouTube or wherever you're hearing this. If you've already hit subscribe, you can move on to rating the podcast. Personally, I'd love 5 stars, but if you think all I deserve is 4, I would take that as well. Now I'm going to get into it and try to wrap up this little mini-series by discussing lectures 6 and 7. Lecture number 6 is about the direction of time. So why do we remember the past but not the future? Why does time go forward? Well, Hawking argues that we can consider 3 arrows of time, 3 ways of thinking about time. The first is the thermodynamic arrow. This is where entropy increases over time. I talked about entropy a little bit in the prior episode, but it means that things generally get more chaotic over time, with the classic example being that your bedroom at the end of a busy week is going to be a lot messier than your bedroom at the beginning of the week. The second arrow of time that we can consider is psychological. This is the direction in which we feel time passing, where we always remember stuff that happened in the past, but we cannot remember stuff that's going to happen in the future. The third arrow of time is cosmological. This is basically saying that the universe expands rather than contracts. The first argument that Hawking puts forward here is that the direction of the thermodynamic arrow determines the direction of the psychological arrow. He goes on to say that when both of those point in the same direction as the cosmological arrow, things get the chance to become more complex over time, and we get intelligent beings. Going into a little more detail about the thermodynamic arrow, entropy increasing means that we generally have many, many more disordered states of things than we have ordered states. So if we start with something ordered, we are almost always going to end at a disordered state, even if the change to get there is random. Moving on to the psychological arrow, Hawking uses computer memory as an analogy for human memory. He does this because computers are a lot simpler than humans, so we can use it as an example to try to learn something about ourselves. Specifically, he says that they are similar in the sense that they don't remember the future, but they do remember things in the past if it's recorded in their memories. Hawking uses this analogy to show that the psychological and thermodynamic arrows of time move together. In other words, the general disorder of the universe increases as humans or computers feel time passing. Basically, it takes energy to record something happening in a computer's memory. This energy is released as heat, where that heat increases disorder of the universe. Using some fun math, we can show that the increased disorder from that heat being released is actually larger than the increase in order from recording something in a computer's memory. And I imagine that works really similarly with a human, where increase in order of the universe of storing something in my memory gets dwarfed by the increase in disorder of energy it takes to do that. So the takeaway from that is that even though a computer mildly increases order in the universe by remembering more stuff, the process to do this generally increases disorder of the universe. All of that means that the psychological arrow of time, which is how humans and computers experience time, increases as disorder increases. So we expect those arrows of time to move together. Now it's time to consider the thermodynamic arrow. If we assume no beginning or end to time, then we could rewind the history of our universe, as I discussed in the first few lectures, to show that matter would have had to have been really ordered and dense early on, where that density was really consistent across the original ball of stuff. Interestingly enough, there also would have had to have been some small discrepancies in density because of something called quantum fluctuation, where those densities end up becoming more interesting as the scale of the universe increases. If that original ball of stuff had perfectly even density everywhere, we would have a really boring universe right now of maybe just smooth gas everywhere. Instead, those tiny fluctuations in density eventually form planets and stars and galaxy clusters and everything else we consider notable. Okay, so the universe started off really smooth and ordered and then moved to lumpy and unordered by forming galaxies and stars and rocky planets, etc. So this, as I already said, represents the thermodynamic era, which is moving from ordered to disordered. And the psychological era of time moves in the same direction, so we always feel things becoming more disordered as well. Well, what happens if everything around you in the universe starts contracting? If the cosmological era of time reversed, would the thermodynamic era also reverse, meaning things get more ordered? Alternatively, would the psychological era reverse, meaning that we experience death before birth? If the psychological era reversed, we would already have information about events happening in the future that we experience. So we would already know numbers that are going to be rolled in roulette, or we would already know prices in the stock market. That would be great for making a bunch of money, but probably not so great for the rest of our lives. Hypothetically, someone could figure out what happens when the cosmological era of time is reversed and the universe is contracting if they were able to jump into a black hole. Of course, none of the information that's sent back to us would actually escape the black hole's gravity, known as this event horizon, and that person would also be stretched out by gravity and turned into spaghetti really quickly. So I don't think anybody's doing this anytime soon. This lecture finishes up with a really fun fact, which is that Hawking actually originally pushed for the view that the eras would have to all reverse together if the universe started contracting. But after some more work by some of Hawking's students, he concludes that it's actually not necessary or required for those arrows to all reverse together. In other words, if the universe were contracting or if somebody were to jump into a black hole, Hawking says that maybe it is possible for the thermodynamic and psychological eras of time to continue moving in their original directions. Quick opinion here is that I think it's really important that Hawking emphasizes when he's wrong here, especially as it's in his own subject matter expertise. Part of the reason it's important is that people can actually understand the right answers and successfully push science forward. The last thing I think any researcher wants is people reading their works a few decades later and getting confused when they find conclusions from that same author which disagree with each other without any explanation. The second reason I think it's so important is that some of these major researchers like Stephen Hawking appear larger than life to most other academics. And it's important to see that they can occasionally be wrong. And if you have some compelling evidence and a legitimate, reasonable theory, people should be encouraged to put those ideas forward, even if they do disagree with someone like Stephen Hawking or Albert Einstein. Lecture number 7, final lecture in this book, talks about the complete unified theory that Hawking and others have been looking for. So the 4 theories to think about when considering a unified theory are going to be general relativity, which explains how gravity works on a large scale, followed by weak force, strong force, and electromagnetic force. General relativity does not use quantum mechanics, while the others all depend on the uncertainty principle of quantum mechanics. So this is going to be the notion that a small amount of uncertainty will always exist at the smallest scale when we're looking at particles. This, as I mentioned in a prior episode, leads to black holes emitting a small amount of radiation and a few other crucial observations. So basically we know that the uncertainty principle of quantum mechanics is real, even if we don't fully understand quantum mechanics at this time. Several stabs at complete unified theories have been put forward so far to varying degrees of success. The dominant theory right now is string theory, which talks about particles not as individual points, but as strings with some specified length and no other dimensions specified. These strings form some sort of shape that we're going to call a particle, and they have a wave going through them. In all likelihood, they are more probable to be a weird shape than they are to be something straightforward like a circle or a square. So while I'm talking here, I'm just going to picture a wavy kind of circle in my head for now, where the outside of the circle is representing a string. But we also know that there are probably millions of combinations for what the shape of that string could be exactly. Interestingly, the strings can also be combined to form new strings, replacing what we originally thought of as one particle absorbing another particle, or those strings can be broken apart to form two new strings, which would be one particle emitting a second particle. String theory was originally proposed in the 1960s, and it was thought that maybe the weak force, strong force, and electromagnetic force were made up of other tiny strings connecting the particle strings. However, these strings would have had ridiculously large tension on them, so this part of the theory eventually went away. Most versions of string theories lead to some infinities when we are calculating their implications, with the idea that these infinities will cancel out if a human or a computer ever sat down to run through all the equations needed. Also, if string theories are really how our universe works, they actually need either 10 or 26 dimensions compared with the 4 dimensions of space and time that we are currently familiar with. The idea behind this is that we wouldn't even notice these extra dimensions because they're curved up into a really small area. As Hawking puts it, a millionth of an inch. The reason we wouldn't see them is because the further you zoom away from anything, the less you notice it. If you picture for a second looking up your home address on Google Earth, and then you slowly back away from it, eventually you're going to lose all the detail of your home, and then lose the detail of your neighborhood, followed by the city, etc. So the same thing would happen if the dimensions were really tiny, where we just don't have any technology to be able to see anything nearly that small. The next question that brings about would be, why are some dimensions curled up, but other dimensions are not curled up at all? Like, why could we see 3 dimensions of space and 1 dimension of time? Why are those dimensions flattened out, but the other dimensions making up string theory are so curled up and tiny? The explanation that Hawking puts forward here, personally, I find a little bit unsatisfying, but I trust him on this, that he's kind of gone through all the options, and this is the most likely. The answer that Hawking puts forward is that this is just the most probable way for thinking beings to develop. For example, if there were only 2 spatial dimensions that are flattened enough for us to see, there wouldn't be any living beings developed. We would have too many issues with really basic things like running over each other, digesting food, all sorts of weird problems. Meanwhile, if there were extra spatial dimensions, those would cause all different sorts of problems, both on the large and small scale. On a large scale, extra spatial dimensions would lead Earth to having a curved orbit around the sun. Eventually, the Earth would get unstable and the planet would get thrown towards or away from the sun, meaning it would quickly get far too hot or far too cold for life as we know it. On a smaller, maybe more important scale, electrons moving around an atom would also be unstable, meaning that the electrons would either escape from the atom or spiral into the nucleus, meaning we wouldn't even have atoms of elements that we are familiar with. So, Hawking says, maybe there are other regions of the universe where different numbers of dimensions have been flattened out and matter exists in them differently. These would have to be well beyond the areas of the universe that we are able to see. And if they had different numbers of dimensions, they would not have any life, or at least not any life as we know it. Personally, I've always been a little wary of multiverse type theories because I haven't seen any clear evidence of why different universes may exist. But I will say this explanation here is going to be one of the clearest explanations I've heard for at least the possibility of their existence. But just because something's possible doesn't mean it's necessarily probable. So I'm going to have to keep reading about these before I back them wholeheartedly. Back to the text, where Hawking asks whether there actually could be a unified theory of everything. To that, he says there are three possibilities. Number one, yes, there is unified theory, and we will discover it at some point. Number two, no, there's no unified theory, but there could be a sequence of theories that we put forward which describe the universe more and more accurately. Three, no, some level of uncertainty will always exist, and we will not predict events beyond that level of uncertainty. In some sense, the uncertainty principle of quantum mechanics means that we're always going to have some level of uncertainty. But Hawking says that what we've done so far is we've always continued finding better and better theories to describe the universe more accurately. And we're likely always going to continue finding better and better theories. This is done by increasing sensitivity of instruments to make better observations, or by making new types of observations altogether. We are not content with some specified level of uncertainty always existing. So Hawking thinks that we can remove number three from the list. This leaves us with either yes, we will get a unified theory, or no, we will just get a sequence of theories describing the universe more and more accurately. Hawking's opinion is that by 2100, we will get a unified theory. Personally, I'm always a bit skeptical of predictions made for time periods well after a person's death because they won't need to defend themselves if they're drastically wrong. But I think Hawking has earned our trust at this point, so I'm willing to hear him out. If we were to get a unified theory, Hawking says, researchers would be able to hypothetically understand the universe really quickly and answer every single one of the big questions that we have. The funniest result of that, I think, is what it would eventually end up meaning to lay people. In Isaac Newton's time, it was possible for an individual to learn the outlines of the extent of human scientific knowledge. Newton was inventing calculus, which is not easy by any means, but it is straightforward enough for high schoolers across the country in modern times to learn. So a layperson in Newton's time probably could have learned it as well. Since then, the pace of scientific development has exploded, meaning that the total sum of human knowledge has grown so much that the percent of human knowledge we are now able to grasp is much lower than the percent someone could have grasped 400 years ago. Additionally, by the time important information makes its way to lay people a few years down the line after discoveries are made, new theories and observations have already been published for leading academics to grasp. So now, small groups of scientists keep up to date with the newest research in their fields, but rarely anyone beyond that gets to know what's going on. The good news about this perspective is that we can expect what we now consider complicated information, accessible only to leading scientists, to eventually make its way to normal people. Eventually, some high schoolers will have a good grasp on string theory. Eventually, if a complete unified theory is discovered, some high schoolers might even understand that. A few hundred years ago, or a few thousand years ago, philosophers were expected to understand all, or at least most, of modern science for the purpose of asking why. More recently, science has gotten too mathematical and technical for many of them to keep up with, meaning students of philosophy now mostly focus on philosophy of language. More recently, Hawking says, science has gotten too mathematical and technical for many of them to keep up with, meaning that most researchers in philosophy now mostly focus on the philosophy of language. But if the unified theory were just discovered and eventually understandable to lay people, then science could loop philosophers back into the discussions of asking things like why the universe exists. If we find the answer to that, Hawking says, then, quote, it would be the ultimate triumph of human reason, for then we would know the mind of God, unquote. Thank you all for listening. I hope you all enjoyed the show. Please rate, review, subscribe on Spotify and Apple Podcasts. Share the show with a friend. Thanks again for listening. Take care.